Hello, and welcome back to Strength of Materials. So my first few videos will be a review of the main topics from statics, which is generally the course people take before the Strength of Materials class. But if you haven't taken statics, that's okay because I'm going to review all the concepts you'll need to know to master this course. So let's get started. So essentially, statics is the study of mechanical equilibrium of rigid bodies, which essentially means you have bodies that are not moving with a bunch of applied forces, and you want to analyze what's happening to that body. Statics problems generally involve analyzing a stationary body, first by drawing a free body diagram, and then by applying the equations of equilibrium to solve for all the internal and external forces and moments. So the first thing you really want to understand with statics are the equilibrium equations. And these equations are very important. Essentially, they stem from Newton's first law. The first equilibrium equation you need to know is the sum of the forces is equal to 0 when you're in mechanical equilibrium. And this is a vector equation. So you can break this equation into 3 dimensions. You can say sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and sum of the forces in the z direction equals 0. For this course, I'm going to be mostly focusing on 2D, although you can extrapolate the ideas we talk about in 2D into the 3rd dimension if you would like, because in real life, most examples are 3D. The second critical equilibrium equation that you need to know is sum of the moments equals 0. If you're wondering what a moment is and you haven't heard that term before, a moment is similar to a torque. Actually, a torque is a type of moment. And the way we define a moment is the same way we define a torque. It's r, which is a distance from some axis of rotation. Some people call it the lever arm, cross product force. And this is a definition from statics. So the 2 equilibrium equations are both vector equations, and they are sum of the forces equals 0 in x, y, and z directions, sum of the moments equals 0. And just like we broke down this force equation here into 3 different equations for the 3 different dimensions, you can do the exact same thing for the moment equation. So you could say sum of the moments in the x direction equals 0, same thing for the y direction, same thing for the z direction. So these are the equilibrium equations, and these are really the fundamental equations when you're studying statics. Okay, so now there's 2 types of situations that you're going to have when you're studying a static body. The first type of situation is called statically determinate. Statically determinate. Okay, sorry, I went a bit off the page there. Essentially, what statically determinate means is the number of unknowns or things you don't know in your system. So, for example, like an unknown reaction force or something along those lines is less than or equal to the number of equations. And this means you can solve the system. If the number of unknowns is less than the number of equations, that means this is a solvable system. We can find the solution for all of our unknowns. Solvable. Bit sloppy. The next type of situation that we can have, which is less fun, is statically indeterminate. And essentially what statically indeterminate means is that the number of unknowns is greater than the number of knowns. And it's greater than the number of equations, sorry. And this means we need to find a way to get more equations to solve the system. So this means number of unknowns is greater than the number of equations. And this is a sad situation because then we need to figure out more equations. We can't use the equilibrium equations. So kind of going back to what I mentioned earlier, if we have a 3D equilibrium, that means we have 6 equilibrium equations if we go back to the previous slide. So if we have 3D equilibrium, we have these 3 equations, and then we also have 3 moment equations. So that means we have 6 equations total. So if we have a 3D body, that means we can solve for 6 unknowns. If we have more than 6 unknowns, that means it's statically indeterminate and we can't solve. If it's a 2D problem, that means we have 4 equations. If it's 2D, then we don't really care about the z direction, right? And that means we have 4 equations, 2 force equations, 2 moment equations. And that means we can only solve for 4 unknowns if we have a 2D problem. Otherwise, if we have more than 4 unknowns in a 2D problem, it's statically indeterminate. So those are just some definitions that you're going to need to do well in strength of materials. And we'll talk more about this a bit later on. All right, moving on to the types of applied forces. So as you can probably imagine, there's many types of forces that can be applied in many different situations. So let's go through all the different types. And I'll kind of group them into different subcategories to make it easier to understand. So the first type of force I want to talk about is a concentrated load. And I'm just going to draw a little cantilever beam here and give you an example of each type of applied force. So a concentrated load is basically the easiest type. Pretty simple, it's just a load that occurs at one point. So we'll call it P, P representing the magnitude of a force, P for point load. A second, more challenging type of applied force is called the distributed load. And that would look something like this. This is how we pictorially represent a distributed load on a free body diagram. What a distributed load means physically is that essentially you have a force that's acting on this entire section of the beam. And this is called a uniformly distributed load. Uniform because it's constant. You can have a non-uniform distributed load, any type of shape you want. Another common shape you might see is like a triangular load. And usually we use Q to represent a distributed load, and the units of a distributed load are newtons per meter. So essentially, let's say this Q here is 10 newtons per meter, and this length that it acts over is 1 meter. That means the total applied force is just going to be this length, 1 meter, times this Q, 10 newtons per meter. And if you do that multiplication, you'll notice that meters cancel and we're left with newtons. And that means that this Q is 10 total newtons of applied force. The third major type of applied force you want to understand is a moment, which I mentioned earlier. And moments are generally applied at a point. You don't have a distributed moment in general, though there are situations where that can come up, and we'll talk more about that later. But these are the 3 main types of forces. So again, we have a concentrated load, a distributed load, and a moment. And this type of beam here that I drew is called a cantilever beam. We'll be doing more analysis of cantilever beams later on. All right, moving on. The last thing I want to cover in this video are the types of reactive forces. So reaction forces. Okay, so there's a bunch of different types. I'm only going to go over the 4 most common types because I could probably spend an hour going in different types and bore you to death, but that's not my goal. So the first type I want to talk about is a roller support. Essentially what a roller support looks like, and these are all idealizations to represent a physical system. So in real life, you're not going to see something that looks exactly like a roller support, but it's good for modeling systems. And that's why this is so important. So again, what a roller support looks like, imagine this is the ground here. And this is how I draw it. Different people draw it in different ways. This is how I draw it. So you have some wheels there, a little triangle, and then you basically have something pinned here. This is our roller support here. Essentially what a roller support does is it has a normal force that acts perpendicular to these wheels here. So we'll have an applied force there. We can call that N for normal force. With a roller support, we also have 2 degrees of freedom. One of our degrees of freedom is back and forth here. We can move back and forth. There's nothing in impeding motion there. And then we also have a rotational degree of freedom. And again, I'm only doing 2D in this example. So we could also rotate back and forth like this. There's nothing impeding rotation. However, we can't move down, right? Imagine if you try to move this roller system down, there's the ground here, which is going to prevent you from moving down. So we have 1 degree of freedom that's being limited when we have a roller. Okay, what's another type of support force? Or another type of support is called a pin support. Pin support. The way a pin support works, it's sort of similar to a roller, but it's even more restrictive. So again, I'll draw the ground here. And a pin support essentially is, imagine you have like a idealization of a beam here that's pinned to something that's stuck to the ground. So essentially, this pin support causes there to be an applied force in the X and Y directions. So you have a reaction force in the X direction, reaction force in the Y direction. However, you still have 1 degree of freedom, right? You can still have rotation back and forth here. There's nothing stopping rotation. You just can't have this beam move back and forth. It's pinned in place. All right, let's move on to our third type of support force. And the third type of support force I want to talk about is called the sliding support. You'll see why it's called that in just a sec. Sliding support. This is the third one we are discussing right now. So let me draw this out. So the way a sliding support looks, and again, my drawing isn't best, but hopefully this kind of gets the point across. Imagine you have like some beam or some column there, and imagine you have like some collar that's wrapped around this beam, and maybe some beam connected to this collar. This is a collar here, just make that clear. So you could probably guess how many degrees of freedom this has. This has 2 degrees of freedom. So this collar basically prevents motion in this direction. So you could say there's a reaction force. The direction, I'm not worrying about the direction right now. I'm just trying to get the correct orientation. There's a reaction force here. This is our XY coordinate system. We have a reaction force in the X direction, right? Because you have a collar wrapped around some sort of cylindrical beam, maybe, for example, here. So you can't move in the X direction. However, you are free to move in the Y direction, right? You have, let me do that in a different color. You have, in the blue here, you have the degree of freedom in the Y direction. You can move up and down, and you also have rotation. You can imagine this rotating like into the page, basically, rotating around this shaft that I drew here. So this is a sliding support. So a sliding support has 2 degrees of freedom. And a support force in one direction here, which I call R for reaction force. All right. The last type of reaction force and support condition I want to talk about is a cantilever beam, which I drew earlier, but I'll get into a little bit more detail. And this is probably one that's going to appear most common in like beam bending applications and things like that. So imagine you have a cantilever like this, and basically you have a beam that's stuck to the wall here. It's completely glued to the wall. And this is the most restrictive support condition that we're going to talk about. So here we have a reaction force in the Y direction, R sub Y, again drawing the coordinate axis here. Anytime you do a problem with statics or materials, it's always good to kind of draw coordinate axes. At least I like to do that. It helps me orient myself properly and define a sign convention. So we have a Y direction. We have a force in the Y direction that's holding this beam up. We also have a force in the X direction, right? Can't move side to side. It's stuck to this wall. So you can imagine there's a force in the X and Y direction. But we also have a moment reaction that prevents this beam from rotating, right? This beam can't rotate back and forth. It's completely stuck to the wall here. So there are 0 degrees of freedom for this cantilever beam. So this is the most restrictive case. So again, the 4 cases we talked about was a roller support, which has a force in one direction and 2 degrees of freedom. We talked about a pin support, which has forces in the X and Y direction and 1 degree of freedom. We talked about a sliding support, which has a force in one direction and it has 2 degrees of freedom. And then this is called a fixed support. And this example of fixed support is called a cantilever beam. But the general case is fixed support. And this is the 4th and the last case I want to talk about. Okay, well, that's pretty much everything I wanted to review for statics today. In the next video, I'm going to be reviewing the method of joints and then doing a real-life example to demonstrate how the method of joints works. Thank you for watching this video, and see you next time.